Yes, welcome back to the next video. We have Ampere circuital law. And what is this Ampere circuital law? Yes, this is a modified form of Biot-Savart law, right? And here we are going to see about what is the use of this Ampere circuital law. Okay, so we can able to find out the magnetic field B value. Okay, and then we are passing a current, we are getting the magnetic field, right? From that we can able to find out the magnetic field here, right? Okay, let's move on to here. The Ampere circuital law give the connection between magnetic field and the current. Okay, the first statement is here wrote, it gives the relationship between the line integral of a magnetic field. Line integral. Why we need to use for line integral? Surface, right? So that we are going to use the line integral. And the total current I, which produce the magnetic field, right? It gives the connection between B and I. Ampere circuital law. And what is this law states that? It states that the line integral of magnetic field B vector around any closed circuit, it's very important. Only in closed circuit it is applicable, not in open circuit. Okay, so at around any closed circuit is equal to mu naught. What is called mu naught? Permeability, right? Is equal to mu naught times the total current I passing through this circuit. So this is a statement we have. It's connect the magnetic field value as well as the current. Yes, so we can write line integral. Generally we have written as integral, right? So if you are putting the circle in the sense, it will denote the line integral, right? Then the line integral B vector dot dl vector is equal to mu naught I. This B and this dl both are vector in forms, right? And these two are exactly parallel. When you are seeing the next one, that time you will see this B and dl as we are taken as tangential way in the circles. And the another modified of the Ampere circuital law is, it states that if the magnetic field B is directed along the tangent, yes, here I mentioned very clearly, B is directed along the tangent. We are taking the tangent of each and every point to the tangent to every point of the perimeter. Suppose if you are taking a circle, then we are saying circumference, that is the perimeter of the circle, right? The perimeter L of a closed curve, and the magnitude of B is constant along the curve. So along the curve the magnetic field value is constant, and for that we can write, just modify these steps as B into capital L is equal to mu naught I, because this line integral varies with this dl component alone, because what we have said, the magnitude of B is constant, so this is constant. Okay, only the variable is this dl, right? So line integral of dl of a circle is changing, say it's in perimeter. That's why I said here the perimeter, right? The perimeter of the circle will give about L. If you are saying in formula, that will give 2 pi r, right? So B into capital L is equal to mu naught I. And the closed curve is called Ampere loop or Ampere curve, and which is geometrically entity. What is called geometric? It has some directions. Geometrically entity and not a real loop, right? This Ampere loop is not a real loop, right? I hope you understand well. And the next video I am explaining about the proof of this Ampere circuital law.